Okay, so welcome to the today's lab. What is the lab number? Lab 3, right? Lab 3 or 4? Lab 3. Okay, modeling of adder and full adder. Okay, in the last class we have seen how to model the multiplexer, right? Okay, now in this particular lab we are going to see how to model the half adder and how can we use that half adder in order to design full adder. Okay, okay. So so let us first of all write the half adder, modeling of half adder. Everybody knows that what are the inputs and outputs for the half adder? There are the two inputs for the half adder, right? This is A, B, and this is sum, and this is carry. In fact, there is a carry out actually, right? Okay, so we know very well that first lab and second lab already we have seen the same a simple half adder can be realized or modeled by using any modeling style. Either the data flow modeling we can go for it, or it may be a gate level modeling, or it may be behavioral modeling. Which one you feel better to write the very simplest of adder? Since you're having two inputs and two outputs. Okay, which is the very easiest way of modeling the half adder? Assignment statements. Nothing but it's a data flow model is very simple. Okay, because we need not worried about the procedural statements. We did not worried about you know. In fact, actually, internal structure also not required. But definitely, we should know the mathematical equation, Boolean equations that we should know, right? So, assuming that we know very well about the data flow modeling, so we write the data flow modeling for this one. Let me write module HA underscore data flow modeling. HA underscore data flow modeling is the name of the this thing. And what are the variables I'm using? A, B, sum, comma, carry. Be careful when you're writing this particular way. Actually, in the habitually, we write the S is a capital and the remaining things are lowercase letters, right? But the same way that you have to write inside of the program also. Okay, otherwise you have to write all the things are lowercase. These are the lower, and this also makes the lower. But intentionally, I put this is a uppercase letter, right? Capital letter. Okay, so let me write above all these things. These are all the input. Input A, comma, B. What are the outputs here? Output, sum, comma, carry. Okay, a simple assignment statement is relevant. Okay, write assign sum equal to A XOR B. Okay, this is the simple Verilog operator I have used. Similarly, I have to use assign carry equal to A and B. Finally, we need to end this module. All right. So therefore, I have modeled this one. I want to test this one. That means I need to write a test bench for it. Okay. Okay. We write the test bench for this one also. Okay, let me write the test bench here. How can we start a test bench? Okay, let me write here only the test bench. So module So because once we write the Verilog program, definitely we have to test it. Okay, without testing that module, we cannot use that module in somewhere else. Okay, so we have to test this one. That's the reason why I'm using HA underscore DM underscore test I'm using. This is the name that I'm using. Okay, next I have to write all the inputs are registered data type, as you know very well, A comma B. Okay, so I want to introduce okay, let it be like that. Okay, it's not a big deal. Okay, so I'm going to take some another way. Okay, uh, generally, whatever the test bench that, whatever the module that we have taken, if you want to test this one, the test bench has to generate signals, right? Test bench has to generate signals. The signals must be connected to the ports of the module, ports of this one. That means I have to, this is my test bench, for example. The test bench produce some kind of signals, right? Okay, this is one signal, it will be generated, another signal is generated for this one. So instead of calling the A and B something like this, we are going to call it as TA, any name that you can write. Okay, and this is called TB. That means I'm going to mention that whatever the input variables that are there, those input variables are represented as a registered data type in a test bench. And moreover, the other names that I'm using for that. That means that particular variables are exclusive to this particular test bench. Okay, we will see what is the advantage of using that one. Okay, okay. So for the time being, how many inputs we have here? Two inputs. That means two variables I have to take in the test bench. Okay, so I'm taking the two variables, the two registered data type. This is called TA and this is called TB. Okay, two input variables. For the two input variables, two registered data types I have to take TA and TB. For example, if the input has, for example, 10 inputs, for example, then what you have to take? 10 register variables, registered data type variables. Am I right or not? Okay. Similarly, how many outputs that are there? Two outputs. That means two variables I have to consider. For that one, I'm using while. While is something like T sum, comma, T carry. Agreed? Okay. Just I included a T's, that's all. But these variables are relevant to what? These are relevant to this particular test bench. Okay, right, good. Now I want to call this particular module. Okay, let me call this module. What is the name of the module that I have given? The name of the module is HA underscore DM, right? This is the instance to this particular test bench. That's the reason why the instance name I have written as M0. Okay, and within that one, I have to write the variables. What are the variables actually? We have a variable A, B, sum, and carry. This is what we have to write. Okay, this is what actually the positional assignment actually. That means the first variable is meant for the A. Second variable is meant for, that means this is what the position is actually. Okay, so the first one is responsible for A. The second one is responsible for B. That means input. The first variable is responsible for input. Second variable is also responsible for input. Third variable is responsible for output. And fourth is also responsible for output. Right? Okay. But see, A variable, B variable, sum and carries I have not used in my declaration of the test bench. Can you see? Okay. That means I want to map, okay, module variable A with this one. Okay. I want to map this one to this one. Similarly, I want to map B to TB, sum to T sum, carry to T. But how do we map this one? This one is done with the help of dot notation. Okay, that means we have to write one dot here dot let me write dot a is connected to what? Is connected to TA. Are you getting this point? That means a variable of the module is connected to the test bench variable TA. That's what the meaning of this one. Okay. Similarly, we have to write another variable. Okay. What is another variable? Dot B is connected to what? TB. Okay. Next, what about the next one? Dot sum is connected to something, and dot carry is connected to something. And okay, this is actually T sum, T carry. Did you get this point? Okay. What I'm doing here by using the dot. Huh? Okay. So you may ask the question, what is the advantage of writing this complex statement? Okay. It's very easy that writing the A comma B comma C and sum is very, very easy compared to this one. But the problem with that one is, for example, as you know very well that what are the variables that we are using? A, B, sum, and carry. This is the module declarated positions, variable position. These are all the positions of the variables, right? Okay. So this is meant for inputs and this is meant for outputs. Okay. Somehow by some means, for example, you change this one to, for example, B here, A here, carry here, and sum here. In the module declaration, something like this you have defined. The same way that you have to define in the test bench also. Same way that we have to define the test bench also. For example, you change this one to, for example, sum here, first of all, sum, for example, A here, next this is the carry here, and this is the B here. This is how you might have declared in the module declaration. The same way that you have to instantiate it in the test bench also. Therefore, that means we have to follow the position of the variable declarations in the modules. Are you getting the point? Whatever the way, so whatever the way that you write here, the same information we have to give in the test bench. See, we are talking about only 2 or 3 variables here. Am I right? Maybe 4 variables. But in reality, it can be maybe 15 or 20 variables will be there in it. But position by position, we are not able to justify clearly. Okay, they may be missing that one variable is connected to another variable of this particular test bench variable. Okay, we are not able to, we may not show that. But sometimes we may be missing actually. That's the reason why we are not going to do that kind of. Okay, instead, this is the right approach. What we know here, for example, even if you write, okay, this is what I have written, right? I'm writing in this way. Dot sum of the sum, comma, dot A of TA, dot carry of T carry, and dot B of TB. If I write like this, it is accepted. Okay, whatever the way that you write here, in the test bench, even if you write like this also, it will acceptable. Why? Because each and every variable is connected to the associated variable of the module declaration. Did you catch that point? Okay. So therefore, so whatever the way that you write, this position is not absolute position. We can write it anywhere, it doesn't matter. Okay. You might have declared in this way, or you might have declared in this way, or you might have declared in this way. It doesn't matter. It will be wherever you want to write it in the port connectivity at any places. It doesn't have any problem. That's the reason why we have to always prefer to write in this is called actuals and formals concept. Okay, this is called actual. TA is actual. Formal is A. A is actually a formal variable. TA is a actual to the test bench. Okay, so either you can use the formals and actual concept, or otherwise positional format also you can read. Okay, so for the sake of please try to habituate these kind of things better than directly copying that variable a comma b and some comma c out. Instead of that one, t a t b, t sum, t carry, that you can write it. Catch the point? Did you catch the point? Okay, right. Okay, let me keep it somewhere. Okay. Okay, now come to the point. Okay, somehow I have written there. Now, what is another thing here we have to consider? So, initial block, right? Initial, begin. What are the variables I can write? So many ways that I have mentioned here, but the simplest way that I'm writing here, please consider this request. Okay. TA comma TB is equal to 2 bit of 0, 0. Can I write like this? As simple as that. Okay. Because the TA is one variable, TB is one variable, I have concatenated, means that I have grouped them in a single thing, and then I can make use of writing the test bench. Okay. So I'm going to copy this one. How many times? I would like to copy this one 3 times. Okay, the first one, and this is the second time. This is the third time. Okay. Now here, what are the things that I need to remove? Okay, these things I should remove, and I would like to write this is called 0, 1. This is 1, 0. This is 1, 1. And at 1 nanosecond, let me take this one. At 1 nanosecond, I would like to take this. That means 2 nanoseconds. At 3 nanoseconds, I want to, sorry. If I write like this, what is the time slot for giving the A, B is 1, 1? At what time this is acceptable? 1, 1? It is a 4, right? Therefore, 1 is added to this one, 2. 2 is added to 2, 4. Okay. So another 1 nanosecond, 5 nanoseconds, I want to remove, for example, I want to stop the simulation. That what I can write? Add 1 to the 4, and we will get dollar stop. Okay. Finally, end this one. And finally, end module. So some more things that are there in the test bench. Okay, some relevant, the useful things that are there. We will talk about those things a little bit later. For the time being, just you consider in this way. Okay, right. Now, for example, if you want to write, if you want to model a full adder, okay, let me write. Let us write the modeling full adder. So everybody knows that what are the way, how many ways that I can realize this full adder. Okay. But for the simplicity, I'm going to write here is okay. Suppose this is what the full adder. How many inputs for the full adder? How many inputs? A, B, C, N. 3 inputs. Sum is 1 output, and carry is C out. Let me write the C out. Carry out is 1 output. So equations are sufficient, right? equations, maybe equations, Boolean equations. Okay, Boolean equations. The one option is there. Another option, is that we can use the behavioral modeling. Okay, truth table. Let me write the truth table also. Okay, by using the input output behavior, we are able to write the behavioral modeling. What is another way? Gate level circuit also. Okay, if you write the structure, the connected gates. Okay, for example, how many gates are required for to realize the full adder? Hmm? Using the gates. How many? For the sum signal, A XOR B XOR CAN. That means the 3 input one exclusive OR gate is required. Instead of the 3 input exclusive OR gate, we take the 2 input XOR gates, two input XOR gates we consider, right? Okay, that's the best one compared to the 3 input because of the various reasons. Okay. The second one is that the scary purpose we use conventionally 3 AND gates, 1 OR gate is required. Total how many are required? Total 5 gates are required, right? But if you go to the lab, for example, people said that, okay, hey, if you want to realize full adder, I have only the hop adders available with me and only one gate is available with you. Okay, not more than that one. Hop adder is available with you, okay, as well as one gate is available with you. Can you make it the full adder by using that one? That's what the question here. Okay, so therefore, so the structure not only, okay, whenever you write this one, the full adder, especially we are talking about the structural modeling, right? Okay, structural modeling. So here what we have seen that, how do we get a structure of a particular digital circuit? Based on the truth table, we develop the mathematical equation. From the mathematical Boolean equations, we are able to develop the hardware in the form of gates. Am I right or not? Okay. The structural modeling requires either the gates or subcomponents. Subcomponents. Subcomponents means it is the component can be realized by lower abstraction also. Okay. For example, half adder the half adder is the one component. Half adder can be looking like a black box, for example, half adder. That half adder can be realized by using the gates. Am I right? Half adder can be realized by using the gates. Okay. We cannot go beyond that level. Okay. We cannot go beyond that gate level, assuming that, of course, transistor level is there, but we are not going to go for that one. The lowest level of abstraction in this particular design is gate level. That means so a complete black box of the half adder, we can go one level deeper as a gate level circuit. For example, if you take the full adder, for example, okay, so if you go one level below that one, it can be realized by using the two half adders. Am I right? If you go for the half adder again in that one particular one, we'll go for the gates. That means there are the two levels that are there, right? If you want to realize full adder, there is a possibility of two levels. One is the subcomponent level, and from subcomponent level to gate level. Are you getting the point? So that means what I can say, for example, if you take about the full adder, for example, okay, what are the subcomponents here? Nothing but it can be possible to realize half adders. Half adders. This can be realized with help of gates, logic gates. I can say the logic gates. Did you catch the point? Okay. For example, you start with half adder only, but don't because my requirement is only develop the hardware half adder only, half adder. What is the structural modeling for this one? What is the subcomponent for the hop adder? There is no subcomponent for the hop adder. Simply directly we will go for the gate level only. Below this one, we have seen only the logic gates only. Am I right? Okay. The structural modeling for the hop adder means gate level circuit only. Okay. The structural modeling for the full adder means it can be realized by using the hop adders or exclusively with the basic gates. Are you getting the point? So therefore, this is what the structural modeling is all about. Okay. So therefore, realizing this particular full adder by using the subcomponents. Okay. Subcomponents means that it is possible to realize by using the gates also. Okay. Another level is below the sub level, subcomponent level. Okay. Okay. So therefore, if the moment if I ask the structural modeling for the hop adder means no doubt that we have to write in the gate level, gate level design. Okay. If I say that if you please try to write the structural modeling for the full adder means, then there is a possibility of you can go with hop adders or maybe directly the Boolean gates, logic gates. I hope this point is clear. Okay, sometimes what I'm saying that sometimes I'm calling as a structural modeling, sometimes I'm calling as a gate level modeling. I hope that the point is clear to everyone, right? Okay. All right. So let us write, of course, hopefully that everyone knows about how to write a Verilog program for the hop adder in the data flow modeling, in the gate level modeling, as well as the behavioral modeling. It is similar to that of what we have seen in the previous classes. Okay. Now we are going to model the full adder by using the structural modeling, not gate level modeling. The structural modeling means in this case is the hop adder. So I would like to use it by using the hop adders. Okay, not gate logic gates. Can you please know what? How can we construct this logic gate? Of course, this mathematics we are this design process I am not going because it is in the BTech course that we might have seen all these things, right? Okay. For example, this is one A input. This is, for example, B input. This is the one hop adder. It will produce two output that is called sum signal, and this is called carry signal C1. Okay. This is the one hop adder 0. Okay. We take another hop adder. We take another hop adder, connect somewhere. Okay. Something like this. Yes. What is the connection? What connection that I have to make here? I have to make here. So therefore, this one is connected to, this one is connected to this one. Okay. Next. This one is connected to this one. This is called CAN. CAN. Okay. Let me remove this one. Now the carry of this one and the carry of this one. Okay. Let me do a little bit here. Okay. This one and this one. What is the easiest way that I can write the drawing? But it takes some crossings that are there. But anyway, this is called sum. Okay. This is what R gate cut here. Okay, not required because the different color, right? Let me write in this way also. Okay, this is yeah. Okay, hopefully you got this point, right? Okay, this is what the box here. Okay. Carry. This is sum. Okay. So let us write the program for this one. Okay. Let us write the structural modeling for the full adder by using the half adders. Okay. Now let us start here. This is actually the main module. Inside of the main module, three components that are there. Three components. One component is a half adder. Two components are half adder. One component is logic gate primitive. So these are called submodules. These are submodules. This is called as gate primitive. Did you get the point? These two are called subcomponents. This is called gate primitive. Okay, that means so what is the difference between these two and this one? What is the difference between these two and this one? So the definition of the half adders, we have defined something like this. The definition of the half adder is defined something like this by the programmer. Okay, whereas the definition of this one is not given by us. Okay, the tool will give you the, that means library have got the functionality of this one. We are making use of that functionality. Otherwise, we would have to write the program for this one also. If it is not a gate primitive, then definitely we have to write, we have to model this one beforehand. Okay, but half adders are, we have modeled beforehand. Now we need not worried about this gate because the gate definition is already, that is modeled by the tool itself. Okay, we can make use of that. Okay, did you catch that point? If you say that as no sir, I don't want to take that as a gate primitive. Okay, if it is a gate primitive, what is the constraint about the gate primitive? The constraint about the gate primitive is first we have to write the output, then we have to write the inputs. That is the constraint. No sir, first I want to write the input first, then I want to write the outputs, for example. Okay, then you have to model on your own. Okay, so let me first, I will take as it is, then I will see, I will show you the what are the modification of it. Okay. Okay, let's start writing this program module. Okay, next, what is the name of this module? Full adder underscore structural modeling. Okay, what are the variables I'm using here? A, B, CAN, sum, and cout. Cout I am writing. Okay. Okay, this is a C carry I have written here, but let me write this is the cout. Okay, right. Now, what are the variables? What are the input variables here? For input purpose, I have used the variables called A, B, CAN. And the output, sum, comma, carry. Okay. Next. Next, what we have to do? We have to call the existing components. Okay. First, I want to call the gate primitive. What is the gate primitive here? OR gate, right? We'll take an OR gate. How do we call this OR gate? Simply write OR. Okay. This is the keyword that is responsible to give the definition of the OR. Sorry, OR gate. So let me give the name of this one is G1. Sorry, G0, for example. What is the output for this one? Can you please let me know what is the output? Cout, right? Okay, let me take the cout. What are the inputs for this one? I have given internal to the circuit is C1 is one input and C2. Okay, let me write this is for the S1 it is not required. Directly it is connected to the sum. For this one, it is required. Let me consider this is C2. This is C2. Now this is C1 comma C2, right? C1 comma C2. Clear? Next. Now we have to call the hop adder. Okay, this is what the hop adder 1, this is hop adder 2. Let me consider hop adder 1 and this is 0, 0 and 1. Okay, hop adder 1. So look at this one. So hop adder, two hop adders I'm using, but their definition is the same. Am I right? Already I have declared as a data flow modeling, and I can use that one 2 times. Right or not? How many times that is there? 2 times. Therefore, 2 times I want to call. So what is the name of this one I have given? Please let me know what is the name I have given. So this is the name. Copy. Paste here. All right. So why I'm copy and paste means that is when you are writing a Verilog programs in your computer, you can not write all the time. Okay, just copy and paste somewhere else also. Okay, don't waste your time to type for the same things and again, right? Okay, right. So this is a hop adder. What is the name of this hop adder in this particular top module? What is the name of this one? Can someone help me? What is the name that I've given there? Anyone in the class? What is the name that I've given? HA naught. Okay, that is HA naught. Output carry I have written, right? Okay, good. C out this is called. This is a C out. Hmm? Okay. Now, this is what I can say that A, B, and sum and carry. Okay. So now what is the A for this one in this case? What is the hop adder A of this one? What is the hop adder A of this is connected to this particular one. That means actually you can observe this one. This is actually A. This is B. Let me take another color better for the sake of completeness. A here, B here. This is the sum here. This is a carry here. Like this is A, B, sum, and carry. Okay. Now, the A of copper A is connected to what? A of the this particular one. Okay, no doubt. What about the B of this one? Is connected to B. What is the sum of this half adder? Connected to S1. What is the carry of this half adder? Connected to C1. Are you getting the point? Okay. Now, therefore, I'm going to write this. I'm going to remove all these things. What is the first position? First position should be A. Therefore, A must be connected. What is the second position? Also input that is connected to B. What is the third input? What is the third variable? It's dedicated for the output that to some signal. Okay. Therefore, that I have written as S1. Next, C1. Did you catch this point, everyone? Okay. A small change I'm asking you, please let me know what is the answer. Okay. If I call the same particular thing, something like this, okay, for example, the same thing, I want to copy and paste here. If I change this value to something like this, okay, in my full adder, just I want to write here is, for example, S1 here and B here, C1 here. Is it a right representation or wrong representation? Syntactically correct or not? What is the syntactically correct or not? If I say something like this, what you should say? Syntactically means that is there any grammatical errors that are there in this one or not? Okay, because we have used the statement, okay, the name of the module we have given, how many variables we have here, right? 4 variables, all the 4 variables I have written, okay? Everything is correct here actually. But when you run the simulation, definitely it will show you the wrong output. Okay, that means you are able to you are able to design, you are able to get the hardware for this, but the output will be wrong. Why it is wrong? Why it is wrong? Because this particular position is responsible for input variable, but this is connected to what? Output. Okay, so therefore this kind of, because we have not correctly follow the position of the variables, that's the reason why it is wrong. If I say that if you want to make it is correct, what suggestion that you can do? Ma? Dot dot notation that we can go for it, or otherwise we can call it as formals and actuals. We can go. What? How can we do this formals and actuals in this sense? In this case, something like this: dot of a is connected to a, dot of sum is connected to s1, dot of b is connected to b, dot of carry is connected to c1. Am I right? This way is okay. Why? Because of course the sum is connected to mapped. The sum is mapped to this one. This is mapped to this one. This is mapped to this one. This is mapped to this one. Doesn't matter when it is mapped. The position is irrelevant to you. Is the point? Okay. So that's what we have to remember in this way. Okay. So therefore, for the simplicity, I'm not going for this particular approach. Okay. Just simply as it is the approach I'm going. Fine. Okay. Of course, this is also not relevant. I'm going to remove this portion as well. Okay. Now we go and write another half adder. So HA underscore DM. Okay, same module, but its name is HA1. What are the variables here now? Anyone help me? What are the A of half adder is connected to what? A of this one is connected to this one. S1 is connected to A1. Next to B of carry is connected to another input is connected to CAN. The output of this one is connected to sum. This is carry. Okay. Okay. Now let me write here in this way. This is S1. Next to CAN. Next to C out, comma, sum. Okay. And finally, and this module. So I have intentionally kept something wrong here. Can anyone suggest what is this wrong? What is that? Some signal. Okay. Actually, we followed the four variables undoubtedly. There is no problem at all. But this position is responsible for carry the some variable. But I have written here is carry. That means output you will get, but wrong output you can see. Okay. Therefore, it is not good. Therefore, definitely we have to remove this, and we have to write here is sum, and this is C out, I guess. Sorry, C out, not C carry, C out. Not C out. What is this one? C2 kada? This is C2. This is C2. Okay. What is the additional thing that I have to write here? Anyone identify? Can anyone help me? Something is missing here. What is that missing part? While we have to declare, right? Very good. Okay. So we have to declare as a while because we have used internally some variables. Those are S1, comma, S1, comma, C1, comma, C2. Okay. I think better we have to take, I think we have to better take this one a little bit further. Okay. Is it clear to everyone? What do you mean by a structural modeling? Okay. How to write the programs by using the already we have declared components and make use of that one into your main program. Okay. Suppose if you write the code something like this, if you're not declaring this one, for example, hop adder you have not declared anywhere, will this program will work? This program will not work. Why? Because so this program in this particular point of it will work. Why? Because hop adder is already available in our library. Therefore, definitely this definition is available. But OR gate. But hop adder is not the case. Okay. But the hop adders we have not declared anywhere. That's the reason why it won't work. That's the reason why I have taken the hop adder program first. Then I have written. I have make use of this one. Okay. Fine. So, for example, if I ask you another simple thing, I don't want to use this whatever already available gate primitive, but I want to define this OR gate by myself. Okay. How do we write this one? That means so what is this one? It's OR gate. Okay. OR gate. What is this OR gate actually? It will take two inputs, nothing but A input, B input, and Y is my output. Okay. What is the functionality of this hop adder? This OR gate. If you apply A here, B here, you will see the output is Y. That is 0, 0, 0, 1, 1, 0, 1, 1. What is the output? 0, 1, 1, 1. What is the Boolean equation for this one? Y is equal A plus B that I can write. Okay. Or logical diagram is something like this. We cannot go beyond this kind of things, right? This is the one way that we can go. This is the second way that we can go. Or this is the third way that we can go, right? These are three ways that are there. Definitely, we can write the three programming models to this one. Three modeling styles for this one. What is the first modeling style? Let me consider this is module. I'm not going to write all the program. Just we keep it something like this. Okay. OR gate or something else I've written. A, B, Y. So what is the wrong in this particular statement I have written here? Can anyone help me? What is the wrong in it? What is the wrong? So actually you can see this is a gate. This is actually a keyword, right? Can you see this is a keyword? In the gate level modeling, we always use the OR gate, OR, small O, small r that we use. This is a gate primitive. Sorry, this is a keyword. So we should not use keywords as identifiers. We should not use keywords as identifiers. Therefore, what we have to do, instead what I can do is that, okay, anyway that you want to write it, this one is underscore gate, let me write here. Okay, whatever the meaningful name that you have, you can use. Okay, now this is where you can observe here, A is my input, B is my input, Y is my output. Okay, therefore I can write what is the equation, for example, A and B, that A or B that I can write it here, assign Y is equal to, I can write it, the data flow modeling. Of course, if it is a data flow modeling, what we can do, let me take again here, for simplicity, I'm writing the data flow modeling. Therefore, directly A or B I can write. I can use this hop adder. I can use this hop adder where? In this particular place. Okay, what is the name that it becomes? Or underscore gate underscore DM Z0. What first I have to write here? First C1, comma C2, comma C out. Did you catch that point? Okay, right. The next, suppose if you want to write the gate level modeling for this, what you can do? If you want to write the gate level modeling this, okay, copy and then paste here. What I can do? It's a gate level modeling, okay, GM. Under the GM, what I can write here? OR gate G1. Okay, as this is called Y, comma A, comma B. Okay, OR gate means OR gate primitive I have to take. and kept this one, and I call this one into the main program. Okay. What is the behavioral modeling for this one? If A is equal to table, if A is equal to B, A is equal to 0, B is equal to 0, Y should be 0. Else if all the things we can write. Is the point is clear? Okay. You may ask you one question, sir. Whenever you write a module for any digital circuit, you are writing the first inputs and then outputs you are writing. Why can't you do it first outputs and then we can write all the inputs? Yes, you can write it also, not a problem. It's your definition. Okay. Suppose something like this. For example, I want to write the half adder, for example. Okay. Why can't it be write in this way? Something like this, half adder, HA underscore DM. Okay. Now first sum, I want to write the sum. And next I want to write the carry. I want to write A, comma B. This is how I want to define. Yes, you can write it, not a problem. But you should mention that output is a sum and carry, input is A and B. Okay. Sir, no, sir, I don't want to write like this, sir. Okay, I'm very much enthusiastic to write something like this. Sum I will write like this, A I will write like this, and the carry I will write like this, and B I would like to write like this. Is it right or wrong? It is also right, but you have to provide what is the inputs here. Input is nothing but A and B. Output is sum and carry. But the same way that we have to use it in the higher module. Okay. If you are using this particular way, you have to call in the same way. If you're using this particular one, you have to call this in the same way, provided if you're using the positional assignment. If you're using the positional placement of the variables. If you're not using the positional assignment, placing of the variables, if you want to use the formals and actuals method, doesn't matter at all. Doesn't matter at all. Okay. So this is how we have to write a structural programming for this. Okay. We stop here today. Okay. The explanation part. Okay. We will go and run this particular thing. Okay. So let me write this is a note. Let me write this is a note 1, note 2. This is the note 1. Okay. Okay. Yeah, better. We can stop the recording.